One of the more difficult parts of pH chemistry is salt hydrolysis. What we can tell is you want to determine if a salt is acidic, basic, or neutral. So let's look at the example of sodium fluoride. Sodium comes from the strong base, sodium hydroxide. Fluoride comes from the weak acid, hydrofluoric acid. What that means then is that when we imagine the salt dissolving in water, we can picture that the sodium and the fluoride would separate in water, but sodium is from the strong base. That makes it a spectator ion. We're going to cancel it out. And when we cancel it out, we're left with just the fluoride. Remember, fluoride is a conjugate base of the acid HF. So we're going to treat it like a base. We can call it a basic salt or we can call it a conjugate base. All right? So we're imagining of the sodium fluoride, only fluoride is important, and we'll imagine fluoride reacting with water to give us hydrofluoric acid and OH. But that's a little bit too complex. Let's cancel out the water aspect of it and treat it like the base. Now, it's going to be very tempting for people to want to write this. You don't want to write this. The fluoride -1 plus hydrogen at equilibrium with the HF. This is exactly what you do not want to do. Let's say no to that. We want to see it in this form, which has the fluoride acting as a hydrogen acceptor in the typical base format where hydroxide is a product on the product side of the reaction. So for basic salts, which we can also call conjugate bases, you have the negative ion accepting a hydrogen, leaving behind hydroxide. We can imagine it in this case functioning as, I'm going to take this away, we're going to imagine it functioning as a hydrogen acceptor, where here comes our sodium fluoride. Sodium fluoride dissolves in water. The fluoride portion is going to accept hydrogen in the same way that water accepts hydrogen during the autoionization process. So here what we can see is the HF being formed, and then back to the F format again. Sodium doesn't seem to be doing anything, does it? It's just watching. It's a spectator. Here's HF being formed, and then we just kind of say this is all about the fluoride with or without hydrogen and one of the waters here. So in this case, we can see what happens. You also have acidic salts. So when we're determining whether ammonium chloride is acidic, basic, or neutral, we can see that the ammonium comes from the weak base ammonia. Chloride comes from the strong acid, hydrochloric acid. And that'll give us enough of a hint right there that we'll realize we expect this to be an acidic salt. Why? Because we're picturing that the ammonium chloride would separate into ammonia and chloride, but chloride from strong becomes a spectator ion. We're going to cancel that out and proceed with just the ammonia. The ammonia will act as the chemical, and in this case, it's the conjugate acid of ammonia. And so, as a result, we'll picture it being a hydrogen donor. There it is, NH4. Donating its hydrogen to water, but let's clean that up. Let's get rid of some of those H2Os. And now we look at it in its traditional acid format. Although it's not an acid per se, it's a conjugate acid. It's an acidic salt. So for the acid salt, we start with an ion that has a positive charge. We make it a hydrogen and the base molecule itself. In this approach, what we can see is that if we had ammonium chloride in water, we would imagine that here's ammonium, there's chloride, the ammonium and the chloride separate in water. Water does its autoionization thing, and it can be a hydrogen donor or a hydrogen receiver. Let's let ammonia be a hydrogen donor, and then it changes its mind. That's what it means to be a weak acid. Even a weak conjugate acid, as it will accept or get rid of them. And once we cancel out all the spectator ions of the chloride and the extra water, we can imagine the reaction looking like this here. Ammonium forms ammonia and hydrogen. Let's imagine that we are looking at four types of chemicals then. Weak acids, weak bases, acidic salts, and basic salts. In the case of the salts, we'll always cancel out one of the ions, In the case of weak acids or acidic acids, they're both hydrogen donors. In the case of weak bases or basic salts, they're both hydrogen acceptors. There's a lot of similarities, but there's some differences too. So here's where we're going to end. When we write the dissolving equation for these, what we imagine is the first one, it says acid in the name. We're going to make it do its acid reaction. That means equilibrium, giving us the hydrogen ion, and what's left? The hypoiodite ion. That's the reaction. Sodium hypoiodite, I can tell by looking at it, is a salt. And the sodium comes from a strong base, so I know it's a spectator ion. I'm going to write down just the hypoiodite ion and treat that with its equilibrium. Being a negative charge, I know it's going to act as a hydrogen acceptor. That makes it a base, a conjugate base of the acid in the previous question. So that'll form HIO when it takes an H away from water, leaving hydroxide behind. Trimethylamine has that keyword amine. And when I see that keyword amine, I'm going to acknowledge that that sounds kind of like a base. And if I look on my list of KBs, I'll find it on the base list. So to be a base, I'm going to make it a hydrogen acceptor. And I'll write that as CH3, 3, N, and I'm going to put the H at the very end with its +1 charge. And that'll accept that from water, leaving an OH behind. However, trimethylamine hydrochloride is kind of the fancy way of saying the acidic salt form. Chloride comes from the strong acid. It's a spectator ion. So I'm going to begin with the same formula, missing the chloride, just with the NH +1 ion when I cancel out the chloride. This is the conjugate acid form of the previous question. An acid is a hydrogen donor, so I will make it donate a hydrogen. That's going to leave it with its base form and a hydrogen that it's donated. Remember, when we take away the hydrogen, we also take away its +1 charge. Study hard.